Next, we'll discuss about the repulsive interaction. As the two atoms are brought together, their charge distributions gradually overlap, just as shown in the figure here. So, this is a charge distribution of two atoms, and when they are brought together, their charge distribution will overlap, like in this figure, thereby changing the electrostatic energy of the system. Okay. At sufficiently close separations, the overlap energy is repulsive in large part because of the Pauli's exclusion principle. As these atoms are come more and more close, the interaction energy will become more repulsive due to the Pauli's exclusion principle. The elementary state of the principle is that two electrons cannot have all their quantum numbers equal. When the charge distribution of the two atoms overlap, there is a large tendency for electrons from B to occupy in partly states of atom A, which have already occupied by electrons of atoms A. So when they are coming close, there is a tendency of overlapping the electrons of energy, that is there is a tendency for electrons from B to occupy the A level, the states of A partly, which was already occupied by electrons previously, and vice versa. So the Pauli's exclusion principle prevents multiple occupancy and electron distributions of atoms with closed shells can overlap only if accompanied by the partial promotion of electrons to unoccupied high energy states of the atoms. So the Pauli's exclusion principle prevents the multiple occupancy of electron distribution. So it is possible only when the electron is get a promotion from the lowest energy to the high energy states. Thus the electrons overlap increases the total energy of the system and gives a repulsive contribution to the interaction. Hence the repulsive interaction become repulsive. An extreme example in which the overlap is complete is as shown in figure here. Here the effect of Pauli's principle on the repulsive energy is, in an extreme example, two hydrogen atom I have shown here one hydrogen atom and the second hydrogen atom, they are pushed together until the protons are almost in contact. So what we are doing is we are trying to push these atoms until they coming in at the utmost contact. So the energy of this electron system alone can be taken from observations on atomic helium, which has two electrons. So this is figure A and this is figure B. This is A and this is B. In figure A, the electrons have anti-parallel spins. So this is 1s parallel and this is 1s anti-parallel. Okay. And so the Pauli's principle has no effect here. So the electrons are bound when they are pushing together, and they will have an energy of minus 78.98 electron volt. But in figure B, these two electrons are parallel. One is parallel and one is parallel for both atoms. So here the Pauli's exclusion principle have to taken in consideration. So here the interaction is possible by a promotion of the electrons from 1s orbital of hydrogen to a 2s orbital of helium. So the electrons now are bound by then minus 59.38 electron volt energy, which is less than that of this value by 19.6 electron volt. This is the amount by which Pauli's principle has increased the repulsion. We have omitted the repulsive Coulomb energy of the two protons, which is the same in both A and B. Okay, so this is how the repulsive interaction increases the, or the Pauli's principle increases the repulsive interaction energy. The overlap energy naturally depends on the radial distribution of charge about each atom. The mathematical calculation is always complicated even if the charge distribution is known. So it is quite obvious that the overlap energy depends on the electrons around the nucleus, and it is difficult to mathematically measure this even if we know the charge distribution. So experimental data on the inert gases can be fitted well by an empirical repulsive potential of the form B by R to the power 12, where B is a positive constant when used together with a long-range attractive potential of the form of equation 9. So this is equation 9. So this is minus A by R to the power 6. And from the theoretical and experimental data, the curve is fitted well with the repulsive potential of the form B to the power R raised to 12. Okay, so the constants A and B are empirical parameters determined from independent measurements made in the gas phase. The data used include the virial coefficients and viscosity. So it is usual to write the total potential energy of two atoms at a separation R as the combination of this and the term appearing in equation 9, that is, which is U of R is equal to 4 times epsilon into sigma by R whole to the power 12 minus sigma by R whole to the power 6. This term is corresponding to this, and this term is corresponding to this. Okay, where epsilon and sigma are new parameters with 4 e to the power sigma 6 equivalent to A. Here 4 e to the power sigma 6 is A. So we will get minus A to the power minus A by R whole to the power 6, just as in the equation 9, and 4 epsilon sigma to the power 12 as B. So this potential is also known as Lennard-Jones potential, which is shown in the graph here. This graph describes the interaction of two inert gas atoms. The minimum occurs at R by sigma, which is equal to 2 to the power 1 by 6, which is approximately having a value 1.12. That is the minimum of this curve occurring at 1.12 value, which corresponds to R by sigma, a value of 2 to the power 1 by 6. Okay, and the curve is steep inside the minima and flat outside. This is steep inside this minima and flat outside this minima, which is quite clear from this figure. And the value of U at minimum is minus E. So the this is U by R by 4A on y-axis. So the value of U is U at minimum is a negative value. Okay, and U is equal to 0 at R is equal to sigma. R is equal to sigma means 1, and this will at 1 this will have a value of 0, and it is quite clear from this expression also. The force between the two atoms is given by minus du by dr. Since this is the equation of potential energy, by differentiating the minus gradient of this potential will give you the force between the two atoms. Other empirical form for this repulsive interaction are widely used In particular, the potential form lambda exponential of minus r by rho is used, where rho is a measure of range of interaction. So other forms are also used, other empirical forms for this expression. Okay, so this is about the repulsive interaction energy in the inert gas systems. So next we'll look at how this lattice constants is evaluated. Okay, if we neglect the kinetic energy of the inert gas atoms, the cohesive energy of an inert gas crystal is given by summing the Lennard-Jones potential over all pairs of atoms in the crystal. So what we are doing is we are neglecting the kinetic energy of electrons, inert gas atoms. The cohesive energy of an inert gas crystal is given by summing the Lennard-Jones potential, which is given by this expression, over all pairs of atoms in the crystal. Suppose there are n atoms in a crystal. Then the Lennard-Jones potential or the total cohesive energy is given by U total is equal to half n for E, and here a summation appears, summation over j, sigma by Pij, are all to the power 12 minus, and a similar term here also. Here Pij r is the distance between reference atoms I and any other atom j, and expressed in terms of the nearest neighbor distance r. The factor 1 by 2, 1 by 2, an additional 1 by 2 is appearing here. This is to compensate for counting twice each pair of atoms. So when we are summing this interaction between pair of atoms, there is a possibility of summing Ij interaction and Ji interaction, but basically both are same. So in order to compensate this effect, a 1 by 2 is appearing here. Okay, the evaluated values of the summation for the FCC structure, for face-centered cubic structure, the summation values is given by summation over j prime Pij to the power minus 12, that is this value. Pij to the power minus 12 value is 12.13188 and Pij to the power minus 6 is 14.45392 for FCC structure. There are 12 nearest neighbor sites in the FCC structure. We see that the series are rapidly converging and have values not far from 12. So the summation series will converge and it won't exceed more than 12 terms. The nearest neighbors contribute most of the interaction energy of inert gas crystals. The corresponding sums for the HCP structures are, so the sums for FCC is given here, and the constants for HCP structures are 12.13229 and 14.45489 respectively. So if we take U total as the total energy of the crystal, so we have already neglected the kinetic energy, so U total will be the total energy of the crystal. The equilibrium value R0 is given by requiring that U total be a minimum with respect to variation in the nearest neighbor distance. So only nearest neighbor interaction is relevant in such a case. So the minimum value of U total or the equilibrium value of total energy is obtained by U total be a minimum, that is the derivative of this total energy to be a minimum. This will give you the equilibrium value of energy. So if you are differentiating du with U with respect to R, and at equilibrium this value will give you a 0 result. So what we are doing is we are equating this du by dt equal to 0. So what we are doing is we are differentiating this expression with respect to R. So 1 by r to the power 12 appearing here and 1 by r to the power 6 appearing here. And when we are differentiating with respect to r, here r to the power minus 13 will appear and a 12 appear on the numerator, and here a 6 appear on the numerator and r to the power 7 and a negative sign corresponding to this power. So we will get a minus sign here and plus sign here, and combining this, and we can write the expression as, if you feel any doubt, you just write it down in a paper, and this is just a differentiation of 1 by of the equation of the expression of the form 1 by x raised to b. Okay, so this will give you this expression which is equal to 0. From this we'll get r0 by sigma as 1 by 0.9. r0 is the value at equilibrium which is obtained from this expression. The same for all elements with an FCC structure. This value is same for all elements which having an FCC structure. The observed values of r0 by sigma using the independently determined values of sigma is given by, for sodium, argon, krypton, xenon, the r0 by sigma value is given here. The slight departure of r0 by sigma for the lighter atoms from the universal value 1.09 predicted for inert gases can be explained by 0 point quantum effect. So this is the predicted value 1.09. So there is a slight difference for these values for these crystals. So this effect is explained by 0 point quantum effect. Okay. So now we will discuss about the cohesive energy. The cohesive energy of inert gas crystals at absolute zero and at zero pressure is obtained by substituting 12 and 4 in equation 11. 12 is equation 1, that is the summation value, and 14 is the value of r0 by sigma, that is the equilibrium value. In equation 11 means this expression, that is the energy of the total energy expression. So if we are substituting these values there, we will get the equation in the form 2Ne 12.13, that is the summation values, and sigma by r whole to the power 12, and here sigma by r whole to the power 6. And when we are putting the condition r is equal to r0, that is the equilibrium separation, then u total of r0 is getting like this, minus 2.15. So we can substitute the value of 1.09 whole to the power 12, not to the power 12, no, all to the power minus 12, because r0 by sigma is 1.09. So we will get u total at equilibrium as minus 2.15 into 4Ne. The same for all inert gases. This is the calculated cohesive energy when the atoms are at rest. Quantum mechanical corrections act to reduce the binding of 28, 10, 6 and 4% of equation 16, that is this equation, for neon, argon, krypton and xenon respectively. So the heavier the atom, the smaller the quantum correction. We can understand, so we have seen that for the correction is larger for lighter atoms. So from this it is clear that heavier the atoms, the quantum correction will become small and small. We can understand the origin of the quantum correction by consideration of simple model in which an atom is confined by a fixed boundary, or atoms are fixed by fixed boundaries. If the particle has the quantum wavelength lambda, where lambda is determined by the boundaries Then the particle has kinetic energy p square by 2m, which can be expressed as h by lambda whole square, where h by lambda is associated with de Broglie wavelength. Okay, by 2m. For the connection between the momentum and the wavelength of the particle, this is de Broglie from de Broglie relation. On this model, the quantum zero point correction to the energy is inversely proportional to the mass. So it is clear from this expression that the quantum correction is inversely proportional to its mass. The final calculated cohesive energy agreement with the experimental values of the table within 7 to 1%. So it is quite clear from these expressions that the quantum correction is inversely proportional to mass. So as mass increases, the quantum correction is less and less. As the mass is lighter and light, the quantum correction is more and more. So it is quite clear from this table. Okay. One consequence of the quantum kinetic energy is that a crystal of the isotope neon 20 is observed to have a larger lattice constant than a crystal of neon 22. The higher quantum kinetic energy of the lighter isotope expands the lattice because the kinetic energy is reduced by expansion. The observed lattice constants extrapolated at absolute zero from 2.5 Kelvin are neon 20 for neon 20 4.644 angstrom and for neon 22 4.559 angstrom. So these are about quantum correction for the values of equilibrium radius or R by sigma value for these metals. Okay, so these are all about the inert gas crystal systems and their interaction energies. Okay.